Namaskar. A very good afternoon to one and all. On behalf of PRL, I, D. Raju, welcome all of you who are joining us today live via WebEx platform, PRL's YouTube channel, and also the scope participants to this, the 61st PRL Ka Amrut Vyakhyaan. PRL came into existence in the year 1947, and so, along with the nation's 75 years of celebrations of Azadi Ka Amrut Mahotsav, PRL is celebrating its PRL Platinum Jubilee year. As part of the Platinum Jubilee celebrations, PRL has initiated several exciting programs and events, and one among them is this lecture series, which is called the PRL Ka Amrut Vyakhyaan, wherein we invite people of eminence in the fields of science, engineering, technology, arts, literature, business, and law to share with us their excitements in their fields of knowledge, their field domains of expertise, so that we can enhance our knowledge. There will be 75 of such Vyakhyans in this series, which started on the 4th of August last year and will be going on until the early next year. All the lectures delivered so far are available on PRL's YouTube channel, and I encourage all of you to view these excellent lectures. I also take this opportunity to request all of you to please stay tuned on all the Wednesdays for the forthcoming lectures as well. Today, the 61st PRL's PRL Ka Amrut Vyakhyaan will be delivered by yet another eminent scientist, Professor Siddharth Ramachandran, who is a distinguished professor of electrical engineering, physics, and material sciences at Boston University, USA. Professor Ramachandran will be delivering his Vyakhyaan on an interesting topic, space, the less explored dimension of light. It is very apt that this Vyakhyaan is part of the Student Conference on Optical Physics, Scope 2022, that is presently ongoing in-person mode in PRL during 28th to 30th September, the 3 days here. I'm sure that this talk will be of great benefit to the scope participants as well. On behalf of PRL, I thank Professor Siddharth Ramachandran for kindly accepting our invitation and agreeing to deliver this Vyakhyaan. To formally introduce Professor Ramachandran to the audience, I will invite my colleague, Professor R.P. Singh. R.P., over to you.
Thank you, Palam. Thank you for giving me this chance to introduce Dr. Siddharth Ramachandran. As our Dean, Professor Param Raju already informed, Dr. Siddharth Ramachandran is a distinguished professor in electrical and computer engineering at University of Boston. He is also affiliated with Division of Material Science and Engineering, Physics Department, Neurophotonics Centers, Photonics Center, and Center for Systems Neuroscience. In fact, he is BTech in Materials and Metallurgical Engineering from IIT Kanpur in 1991, and subsequently earned his doctorate in Electrical Engineering from University of Illinois Urbana-Champaign in 1998. He then joined Bell Labs as a member of technical staff and subsequently continued with its spin-off, OFS Labs. He moved back to academics in 2010 to Boston University, where he's professor, a now distinguished professor. And his research focuses on optical physics of guided waves and optical fibers. One of his most notable works is designing of optical fiber for optical vertices and using it to increase the data transmission capacity of optical fiber. He serves the optics community in several capacities, including as a topical editor of Optica. His achievement and honors include Fellow of IEEE, OSA, Optica Now, SPIE, International Society of Optics and Photonics, Visiting Fellow, UK Royal Society of Engineering, Distinguished Lecturer, IEEE, Distinguished Member of Technical Staff, OFS. And his area of research interests, along with guided wave optics and optical fibers, include nonlinear optics, ultrafast and quantum photonics, fundamentals of light-matter interactions, super resolution and brain imaging, classical and quantum networks. So with this introduction, I invite Professor Ramachandran to deliver his talk. Over to Professor Siddharth.
So can I start now?
Yeah.
Yes. So thank you very much for the very kind and extended introduction. It took me down memory lane to learn that I actually did my BTech all the way back in 1991. I suspect that a good part of the SCOP student participation was not born then. So, welcome to a new world. More importantly, I feel honored and honored to have the opportunity to present at in this very interesting series that commemorates 75 years of India's independence. So, without further ado, let me go ahead and start sharing my slide, and then we can start the talk. Okay. I would just request someone to confirm that they can see my
Yes,
my
yes.
slides
Yes,
in
we
the
can. We
presentation
can.
mode. Excellent. Okay, so let's get started. The topic of today's lecture is space, the less explored dimension of light, as the title says. So what does this mean? So let's jump right in. If we were to try to understand what this is, here's a brief outline of what I'll be talking about. Essentially, I'll be talking about spatially complex light, and I'll start off by first defining what I mean by that. Spend a little bit of time talking about what people have done in the past, and then get to perhaps one of the important aspects of spatially complex light. And the point here is that we are all, whenever we think of light, we think of a Gaussian beam, something that looks like a spot. But of course, we're going to look at something much more complex than that, both in amplitude and phase. And it turns out that these not only have interesting properties, which is the reason why I'm talking to you today, but they also have some problems in that they're inherently unstable. So I'll spend a good part of my talk talking about how one can solve that problem and how we have solved that problem, which is why this has become more interesting. No talk in optics can finish without a segment on nonlinear optics, and so I'll spend some time talking about the nonlinear optical applications, sorry, the properties, and then I'll jump into applications. Okay, so since we're all familiar with the Gaussian, let's start with it. Here is the solution of the Helmholtz equation. I have lumped in all the radial and propagation distance, mainly r and z terms in some kind of an amplitude, mainly to show that the main part of this that we get, that we often know about, is we have a propagating phase, but we also have a radius of curvature. And so if I try to propagate this over space, let's say I put a lens, then I get some diffraction, and I can define something called a k vector, which is the direction in which propagates. But I also know that the k vector is normal to the face front, so that means that part of the beam is actually trying to escape, and this is the phenomenon we call diffraction. Okay, so because of the fact that this diffraction happens, because of the fact that I can never maintain a beam of the same size with propagation, the reverse of that is also true, in that if I try to focus it down and I try to do microscopy with it, then at some point I will fail in doing microscopy. Here's a Gaussian beam, I go through this, here's the sample I'm trying to see, and obviously it's all kind of blurred, right? So now let me tell you about one solution that people came up with for this about almost 20 years ago. And now pay attention to this Gaussian beam, because I'm going to play a very small animation here. If I take this microscope and then just add a grating line, you saw this grating line moving back and forth. I'm going to do this again, right? If I move this grating line back and forth, and if I do a little bit of calculation, then that same image becomes much sharper. And this area is called SIM, or it stands for Structured Illumination Microscopy. So the point I'm trying to make here is that the moment I introduce some kind of spatial structure in the Gaussian beam, I'm already getting some benefits, or something different at least, and then sometimes it's beneficial, right? And that's kind of the motivation of this entire talk. Okay, so let's take that a little further. Here's a Gaussian beam. Now I'm going to focus it down. If I focus it down, I know that if this is the polarization will bend. And so as a result, at this point, you can see that a component of this polarization and this polarization will destructively interfere, which effectively mean that I self-aperture this beam. This is in fact a fundamental problem with Gaussian beams, and that's the reason why we can't get to the so-called Abbey limit for focusing with these kind of beams, the moment I include this vector nature of it. Okay, so now let's start looking at some structured beams. Here's an example of a particular structured beam that's called a radially polarized beam. This has an optical vortex. It has a vortex for polarization, which basically means that at the center of this beam, the polarization is not defined, it's a singularity. Do the same exercise and you find something very interesting, that in the direction of propagation, you have a very strong field. Right, so that's already kind of very weird, because we always learned in our optics textbooks that light's polarization or the electric and magnetic fields are normal to the direction of propagation. So, but at this singular point, you actually get this kind of a weird polarization. There are lots of different reasons this is useful for. Here's one reason. If I try to do resolution, imaging with this, then here's a Gaussian beam and here's a radial beam. And then if I start blocking this aperture, making a tinier and tinier aperture, you notice that the Gaussian beam can't really do very well after a certain point. And that's because of this effect. At some point, it starts self-aperturing, whereas the radially polarized beam can get to very, very small resolution, or very high resolutions. Note that here it's 155 nanometers for 1300 nanometer light. It's much, much smaller than lambda by 2, which we usually think as the limit. So let's get a little bit into it. So what are these states? I've just, right now, I have told you in an analog fashion that these are these complex states, right? Well, they are higher order states. What are higher order states? Higher order states are states that exist in any resonator. Here's an example of a resonator that I especially found because I figured I'm giving a talk, at least virtually, in that part of the world. Apparently, there is this stringed instrument, which is one of the most ancient string instruments that have existed in the Kutch and the Sindh region from many years ago. What do string instruments do? They're resonators, which means that they have all sorts of different resonances. And these are all the different states in which I can have mechanical motion in this resonator. This is my ground state, my fundamental state. This is the same thing as my Gaussian beam. And here are all these other more funky, weird beams. And these are the kind of beams that we want to talk about today. If you look at the another form of a resonator or a potential, if I go into solving for the energy levels of an electron in a confined potential, let's say an atomic potential, then we also know from there that not only do we have different energy levels, but we also have electrons that can carry a specific amount of spin and orbital angular momentum. And the amount of spin and orbital angular momentum they carry depends on the energy level that we start with. So this is all stuff that we know at various stages of our high school to undergraduate physics lectures. So now let's come back to light. This was the light beam that I told you about. It is also a solution to the wave equation, much like the last two solutions I showed for a stringed instrument, as well as for electrons in confined potential. And as I said, this is my Gaussian beam. This is what I have mostly concentrated on. So then, of course, if I solve for this, then I should be able to make the analogy with atomic states that these kind of beams carry spin angular momentum, which is essentially a fancy way of saying that it carries left or right circular polarization. But of course, it has all these other higher order states which show up as helical phases. What do they look like? This is what they look like. If you notice that as I increase the L in this, then the phase front becomes more and more, turns more and more per oscillation. And now if I look at the wave vector at each local point, you notice that it's starting to do something very weird, right? The wave vector itself, the momentum vector of light is itself rotating in a rather funny fashion. The end result of this is that these kind of beams do have orbital angular momentum also, exactly like we learned for atomic physics. This is what a beam looks like. Orbital angular momentum for light manifests as a phase. So how do we see this? There's actually a very nice, simple way to see it. We see phase always with interference. So if I interfere this beam with an expanded Gaussian beam, then on the camera in the lab, you can get these very beautiful patterns of spirals, and the number of parestheses I have on the spiral is essentially the orbital angular momentum of this beam. These are very, very interesting for a lot of applications because of the fact that they carry orbital angular momentum. Stephen Hale demonstrated that you can do nanoscale microscopy with a technique called stimulated emission depletion, which is STED microscopy. He won the Nobel Prize for it in, I believe, 2014. Because they carry this kind of angular momentum, it turns out they're actually very useful for machining. They carry angular momentum, so you can actually transfer them to particles and make the optical wrenches for it. And people are actually trying to use it for doing DNA sorting. And a lot of other applications. There are a lot of states. You can use it for secure quantum communications, rotational sensing, etc., etc. So this is about what happens in the azimuthal direction. There is another direction in which I can have complexity, of course, and that is in the radial direction, right? So far I was telling you everything about what is happening to the beam when I do something weird in this direction. What if something happens if the beam does something weird in this direction? Well, I mean, this function, as you may be able to surmise, looks very much like a Bessel function. So these are called Bessel beams for that reason. If I solve the diffraction equation for this, I get something very interesting, which is that a Gaussian beam that diffracts very, very quickly for a given size, a Bessel beam, at least the center spot kind of maintains itself for a much longer distance. So immediately you can see that this is actually very useful for having pencil-like foci for a lot of different applications, right? Another interesting thing about these Bessel beams is that now let's take this Bessel beam and then let's put some kind of an obstruction in it so that I kind of try to block it. And then let's now move this imaging system behind. And then we look at a movie of this imaging system moving behind. You immediately see that the obstruction basically disappears. So these beams are basically self-healing. It's nothing special about putting them in the center. If I put them on the side, the same thing happens. So a quick explanation as to what's happening. Bessel beams are essentially plane waves that travel in a cone. And so if I look at it in the ray picture representation, if I put an obstruction here, it becomes rather obvious that if I go away from it, I no longer carry any information about the obstruction. I get loss, but I do not get loss. I get loss of power, but not loss of information. So what's this useful for? Well, it has been used for doing light sheet microscopy, which is one of the ways by which one can do very high-speed microscopy these days. It has been used for precision machining. Remember, it has a very long focus spot, and so that obviously is useful for machining very, very deep in a very precise manner. And also because of the fact that these beams are effectively very, very large, they can carry a lot more power. So people have used them to do power scaling of lasers also. Okay, so now let me come to a next part of it. So far, everything I mentioned was in free space. The question we wanted to ask is, well, free space with lenses and propagation is essentially a cylindrically symmetric system. Yeah, we know that there's another cylindrically symmetric system that is ubiquitous, which is an optical fiber. So the question we want to ask is, well, I mean, do these states exist in an optical fiber? Can we use them in an optical fiber? All right, so very simple. Let's go here's an example of a fiber that we bought from Thor Labs, very standard step index fiber of a very standard kind. I solve Maxwell's equations. I find this solution. This is my ground state. But of course, again, I have solutions of various different orders. And there are two types of orders again, because it's a 2D system, right? There's a radial order. So these are resonances in the radial direction. And there's an azimuthal order. So these are resonances in the azimuthal direction. And M and L, where L, remember, was something that I told you earlier about. So let's get to that in a minute. This is one mathematical representation of it. We all know that we can usually combine eigenstates that are degenerate to create other mathematical representations. So if we do that, then we get these kind of modes that are usually called orbital angular momentum modes, because indeed they have IL and this helical phase, or they're also called vector modes if I write it in a different representation. So long story short, yes, indeed, all of these exotic states exist in fibers. These exotic states already clearly have some properties that are different from a Gaussian. And so the question is, well, if they're in a fiber, can we, exploit them because of the fact that they're in a fiber for a variety of applications? That's the question we want to ask, and this is the problem we encounter. And so now this problem is a problem that we encounter not only in a fiber, but practically in every system. In fact, this is one of the reasons why all these higher order states that I've told you about, while very, very interesting, also tend to face this problem that limits their applications sometimes. And what is that problem? Well, that problem is the problem of scintillation, turbulence, mode coupling, call it whatever you want. We know this phenomenon very well, right? On a hot day, the ground is much hotter than up there. That means the refractive index changes along this direction. So that means if I try to look at this tree, then this is how I was supposed to look at it, but all these waves get distorted. So I effectively see a mirror image of it. That's a classic mirage. All of you have seen a mirage, of course, on a dry day, on a dry, hot day, right? And so this is a distortion problem. Anytime I try to send a beam of light through a medium that has varying refractive indices, either due to temperature or atmosphere or something, or moisture, then I get distortions. It turns out that these distortions are obviously much worse for higher order states than for lower order states, because if I have only one state, I might still get one through. But if I have many, many states, then they may start getting mixed with each other. Okay. So same thing, of course, is going to happen in a fiber also. If I here's one of the many solutions I was telling you about earlier. If I send them through a perfect fiber, of course I get it out at the other end. But there is no such thing as a perfect fiber. Every fiber has some perturbations. And when I send these perturbations, what happens is that the sum of all these states, light basically creates every one of these states due to these bounces and irregular bounces. And the sum of all of them essentially give us what's called a speckle pattern. So scintillation and mirages in free space are the same things as speckle patterns in optical fibers and in scattering media. And so, of course, this is not true only for our optical fiber, it's also true for the scattering medium. In fact, this is the main problem we try to solve when we try to do deep tissue biological microscopy, because tissue, unfortunately, is a highly, highly, highly scattering medium and does basically the same thing. Okay, so so far I've been somewhat heuristic, so let's get a little more specific here. This problem that I have defined is essentially a linear distortion, linear matrix multiplication problem. So what do I mean by this? Let's say I can represent this field or a collection of these fields together forming an image as a vector. And let's say this vector is different electric field in the x direction, electric field in the y direction, electric field in for or maybe for mode 1, for mode 2, for mode 3. It doesn't matter which basis you choose. This is what I was trying to send. This is my tree. This is this mode. Yeah, the medium, whether it's this one or the fiber, essentially did this to it. It added a massive matrix to it. Now, in general, it's not always true, but to a large extent, you can assume that this matrix is unitary. What does that mean? That I don't lose any power. That means all these x1 to xn essentially rearrange themselves. And this figure kind of shows that, right? The light never escapes out of the fiber. This mode becomes this mode becomes this mode, etc., etc. So they exchange energy between each other in some weird fashion, but at least I don't lose energy. So that's essentially a way of saying that this matrix is unitary. So those two things happen, and so the result is this. This is what I'm showing you here. This is what this person is seeing here. This is what we are seeing in a mirage, right? So now that we have a nice mathematical way of describing this distortion, let's get to the next part of our talk, which is to ask, what do we do about this? This seems to be a very fundamental phenomenon. Can we do something about it? In two different ways. And I'm going to answer this question in two different ways. Well, in one way is, well, it's a property and it's a problem. Let's try to exploit the problem itself. And then the next step, of course, is to ask whether we can avoid it altogether. Because the problem with, of course, exploiting it is that I can't get any of those, unique properties I was telling you about these modes right at the beginning of this talk. Yeah. All right, back to our matrix. This is the matrix. Well, actually, the problem is actually pretty simple, right? I mean, all of us have done enough linear algebra to know that if I take this, then if I can somehow measure this properly, then I should be able to invert this matrix. Well, guess what? I have essentially defined what we do in astronomy all the time. In astronomy, your twinkling stars are because of this matrix, because of atmospheric perturbations in this matrix. And so those are all phase perturbations. So if I have some kind of an adaptive mirror that can completely do the reverse wavefront distortion, which is another way of saying that it can invert this matrix, then I should be able to clean it up and be able to see what I want to see. And it's a very common thing that we do all the time, right? Um, the reality is a little more complicated than that because, of course, this linear system is not as clean as I have written. It has noise in it. So when it has noise in it, it becomes a little more complicated. One has to, do some kind of a least square estimator, maybe use steepest descent algorithms, and maybe these days more and more use some kind of machine learning algorithm. But at the end of the day, I just want to kind of find a matrix which, when I apply to my signal that I have measured, will be able to recover the signal that I had to start with. So in telecommunications, actually, that has been very, very well developed. Imagine that I have all these different transmitters. I have signals coming out of it. These can be electromagnetic waves in the radio wave regime, or it could be light. It doesn't matter. Each of these basically kind of scatters light into all these different states, right? So this is my whole mixing, the turbulence that I was telling you about, that happens all the time. And this is why I can never get this signal here, this signal here, this signal here. Everything's mixed up, but it's mixed up like this. The nice thing about this is that if I can somehow measure the amplitude and phase, that means if I can measure this absolutely accurately, then I can actually estimate the matrix I need and apply that and then get my original signal. So this thing is called this technique is called BLAST. It's also called multi-in, multi-out. Those of you who have more of an electrical engineering background would be very familiar with this term called MIMO. This is the processing that it was developed in the late 90s, actually, to be very robust. And this is the processing that essentially made all our smartphones possible. Before this, none of our cell phones, especially the smartphone variety, could have had the ability to get the amount of bandwidth we get today. And that was only because essentially we solved this interference problem. And in this case, the interference was, much more mundane. It was not the kind of interference I was telling you about. It was about a base station from where a wireless signal is coming. It would bounce off one building, bounce off another building, bounce off your window, bounce off your car, and then get to your cell phone. Obviously, what does that mean? It is interfering. All these different parts are interfering. So it's exactly the same problem. Yeah. So that's how they solved it. And of course now in optics also we've been trying to use similar digital signal processing techniques to solve this problem. It's a matrix inversion problem. So if I do the inversion of the matrix at the beginning of an optical fiber, then at the other end, I should be able to get a very clean image. So this is basically, if I use this analogy, this is saying that since I know this, I'm never going to send this. I'm actually going to send the inverse of this times as this, so that I always get this out at the output, right? So this is the time reversal of the entire process. People have shown that you can do that and essentially focus images through an optical fiber, a multimode optical fiber. People have shown that you can do it for 2-photon imaging. And very interestingly, these speckle patterns that we all call random is obviously not random. This is a function of all the interference I was telling you about. And that interference is between modes, and it's a function of wavelength also, which basically means that every one of these interference patterns, they're like fingerprints for this wavelength, right? For each different wavelength, it looks different. So that means if I can analyze this properly, I can invert this matrix and just use this camera image to predict what wavelength this light would have been. Right? So very simple way of making a spectrometer, if you will. This has been taken to a much more complicated level by essentially using this instead of creating these random patterns, to essentially use those random patterns to essentially generate random numbers. Obviously, the ability to generate random numbers is extremely important because that is the basis of the clocks of all our computers that run. Electronics can simply not do something at the speed at which optics can do these kind of things. So yet another example of where we have used this instability. Okay, I'll close this section about talking about how to use these model instabilities with something that is just emerging. As you can see, this paper just came out in 2021, but it's becoming, and I mean, there have been other papers. This is one representative paper in this field. There have been other papers in some time. But to me, this is a very interesting topic that's actually emerging, right? So let's say these are all my modes, and I'm just schematically showing them as different amplitudes of different vectors here. Then in an optical fiber, remember what happened? It went from here to here. Maybe sometimes it went straight. Sometimes it scrambled into other modes. Sometimes it scrambled a lot into other modes, and so on and so forth, right? That's basically what happened in this system. There's one additional thing that happened also, which is, and that's something that I have not talked about yet. That's my next section, or actually, no, two sections away. When I talk about nonlinear optics, this transfer may not have been linear. It may not have been that nice matrix multiplication that I was telling you about so far. This may also be nonlinear, which means this may be due to this amplitude times this amplitude. In linear algebra, it'll always be this plus this, right? This with the coefficient plus this with the coefficient. But now it could be times these two amplitudes. It could be square of something. It could be cubed of something. So in a sense, this could not only be a linear matrix multiplication, but a nonlinear matrix multiplication that also happens at high enough power. Okay, the reason why I took so many words to describe this is because what I have described here is essentially what's called a neural network. The way people do machine learning, and we all know machine learning is very important these days, right? In data sciences. The way machine learning is done on chips is that digitally, I literally take billions of these, make them talk to each other, sometimes with a nonlinear function, sometimes with a linear function. I do it over and over and over and over again. And essentially, you can show that if you do it enough number of times and you have this highly complex stochastic system, then you can actually learn from it and use it for rules. And that's essentially the idea of machine learning. This suggests, and machine learning is great. We're all using it. In fact, I'm sure many of you are using it also these days, or if not, everyone plans on using it because it seems to be such a nice tool to do computation, especially of systems that we don't understand very well. But machine learning is also a huge problem that I basically need a billion different processes digitally on a chip. So in fact, machine learning is one of the most power hungry things that we have come across. I'm sure you've heard of news reports about how, what is this? The Bitcoin revolution, which is all based on machine learning, is essentially dying because of the fact that it's consuming more energy than even airlines these days. So this is a serious problem. But I just described to you an optical system where the physics does all of these matrix multiplications for me, linear and nonlinear. That sounds very attractive. So here's actually the first example of having done this. People have taken spatial light modulator, and what they did is they basically trained this system. So you send this, you get this speckle pattern, right? But imagine that I send this image, I get this speckle pattern, another image, I get this another speckle pattern, and so on and so forth. And if I can correlate all of those, then that's the essence of machine learning. If I now send a new image, will this decision system be able to predict what that image was? So this paper was essentially showing that if you were to just do a simple classification between lungs that show COVID infection and no COVID infection, obviously a very topical thing to do in 2021, then this system will be able to tell us whether that worked or not. The accuracy of it was 81%, not as good as what computer chips can do, and I think there are lots of improvement to be done in time. But here's the fun part. If you use electronic chips, NVIDIA makes some of the, I'm sorry, there should be an I here. NVIDIA makes some of the fastest, best chips for machine learning. Gigaflops, I'm sorry, there's a typo, there's a P here. A gigaflop is essentially, flop is a computer operation. Then, this consumes about, it takes about a joule of energy to do 77 gigaflops of operation. This optical system is 14 teraflops per joule. So it consumes 180 times less energy. I'm cheating a little bit. I didn't include the energy of this processing system. I did not include the energy of the laser, etc., etc. But you get the picture. Why? I can use the complexity of a highly multimodal system, perhaps to naturally get the physics to solve my computation problem rather than trying to do it brute force with DSP. Okay, that ends that part of my talk. Now let's move to the next part where I'm saying, well, I mean, all that was good. Can we avoid these instabilities? We're back. This is the mode. This is the mess that we get at the other end. And so now let's go and look at why this mess happens in a little more detail. It's essentially mode coupling, and a mode coupling theory, many of you may have studied in different contexts, whether in the context of electron excitation. So these are, the work functions or not. It's basically two orthogonal fields multiplied by a perturbation. And the best part of this is that this seems to be very sensitive to the propagation constants or the eigenvalues of this system. And so it seems to be that, very simply, if I just separate these eigenvalues somehow, I should be able to minimize coupling. So let's go and take this analogy further. A particle in a box, we know that as we go higher and higher order states, the states get naturally separated. That means in an optical waveguide also, as we go to higher and higher order states, things get separated. Here's a multimode fiber again. I put a lower order state, then this is the mess I get. This is the mess that we've been seeing all along, right? But now if I somehow put light only in this state, this is a movie that's actually running right now with me shaking the fiber, and it remains rock solid, right? So that's obvious. There's a natural solution to this as long as we use very high states. That was again the radial. If you go to the azimuthal, again, like I said earlier, I have different different energy levels have different spin and orbital angular momentum. In atomic physics, we also know that there's this very classic LS spin orbit coupling, and the same thing happens in a fiber. In that each of these states essentially splits into doublet states. So it turns out that I will skip this part, but basically, if you make ring core fibers, then you can make sure that this splitting is large enough so that these states are stable. Okay, so let me give you a summary of the stability of states in a fiber. If I take a Gaussian state with this polarization, it's ended through a straight fiber, then everything remains fine. But the moment I bend this fiber, my linear polarization becomes elliptical because of birefringence. And the best part is then when I take it on a 3D state, it becomes completely crazy and goes crazy. I'll get in a minute to what this means. So now let's look at a low angular momentum state in the linearly polarized domain. Then when I send it even through a straight fiber, it completely gets messed up. Now let's look at the vector states I told you about. They seem to maintain themselves in a straight fiber, but they completely die in a bent fiber. And the same thing is true for the orbital angular momentum state. It's nice in a straight fiber, the bent fiber messes it up. Now let's go to a much higher vector state, much higher L vector state. Notice that it is able to maintain itself through a bend also. But then when I go through a 3D change, it completely gets messed up because it rotates. And finally, if I go through an orbital angular momentum state of a very high angular momentum, then I find that it completely maintains itself throughout the entire system. So the story here is that Gaussian modes. So now this is funny, right? Now I'm saying the opposite of what I started with. The fundamental state is actually the most unstable state. And then states that are defined as these linearly polarized states are also pretty unstable. But as I go to higher and higher L, these modes become very stable. And it turns out that if you look at the perturbation equations in these calculations, it turns out that the reason it becomes stable is the same reason a spinning top doesn't fall. In that these beams have such high angular momentum that a small perturbation doesn't mess it up. And then finally, I mentioned that for some reason, high angular states in the vector basis is supposed to the OAM basis. One of them is more stable, the other is non-stable. And that's because of this classic, what's called the Pancharatnam-Berry phase that comes because light also accumulates a phase due to geometry of path, and that phase depends on angular momentum, is the reason why this happens. And so essentially, in the end, this is the state that's the most stable state here. Okay. One other interesting thing about this system is that one way to describe these fibers is that, I had these four states for any given L. It could be plus L and plus sigma or minus and plus, the four different combinations of spin and orbital angular momentum. And in our design, we basically separated them out, which means that each of these is individually stable, which means I should be able to create a superposition of them, and then I propagate this through an optical fiber. Then what happens is that because they have different propagation constants, this polarization actually rotates as it propagates. Now that's actually very interesting if you think about it, because I have described what is called optical activity. Optical activity is something that we know we find only in chiral molecules, or if we take a material and actually intentionally twist it, that's when we get optical activity. Optical activity is essentially a breaking of mirror symmetry. In fact, this is the thing that happens in a lot of biological molecules. It also happens in sugar water, but it's not supposed to happen in glass. Glass is a purely isotropic medium. Right? So in this case, what's happening is clearly because of the spin orbit interaction based splitting, I actually get an isotropic medium to become chiral in nature. And the best part is it's engineerable because the rotation rate depends on this. This is the splitting, and this splitting depends on orbital angular momentum. Right? So by changing orbital angular momentum, I can actually change the of light, I can change the chirality that the medium imparts to light. The final thing that I wanted to kind of touch upon on this on the scheme of on the scheme of linear interactions is an effect that we actually found very recently. We're still in the process of publishing it in a journal, but we're very excited about it. We have always learned that a waveguide is, here's my step-in waveguide, and the states are always, guided. A bound guided state exists inside this waveguide, right? Which is another way of saying that total internal reflection is satisfied. In fact, that's what we've learned. All waveguides are waveguides because total internal reflection keeps light inside it. So that basically means that if light is here, then it'll leak out. It's a radiation mode. It turns out that actually, if I go and look in a cylindrical system, the potential of this, then this essentially behaves like the angular momentum of the photon creates a change to this attractive potential, which is my refractive index. Long story short, what this means is that if the orbital angular momentum of light is higher, then this state actually experiences what's called a centrifugal barrier. So it actually prevents itself from being from escaping. This effect that I have described is actually very well known in nuclear and atomic physics. And in fact, Phil Buckbaum wrote these classic papers in the 1980s that said that if an electron has very high angular momentum, then the ionization energy has to be higher than whatever I calculate. It's the same thing. It's a barrier effect. A simpler explanation, or perhaps a more intuitive explanation for this, is a low angular momentum state has radial wave vectors, so it kind of diffracts out a lot. Remember my very first slide that said, the k vector tells me the rate of refraction. And a high angular momentum mode kind of just, it does still have a high transverse wave vector, but since it's azimuthally oriented, it just kind of keeps going round and round, and effectively it is low loss. So this basically means that I can get guidance beyond beyond cutoff. That's an effect that we are very excited about because this whole game with multimode fibers and stable propagation has been about seeing how many modes I can get out of a system, and the maximum that people have ever been able to do is 12 to 24 out of 10 to 10 hundreds of meters to a kilometer of fiber. This new effect gives me guidance of up to 50 to 60 different modes because of this new guidance regime that we have discovered. Okay, so that was a summary of all the different linear properties of the system. So now let me, before I actually go ahead, I'd like to ask how much time we have.
We have about 10 to 15 minutes.
Okay, 10 to 15 minutes. So then I'll try to race through. I actually went a little slow because I got caught up earlier on the machine learning part. But one very simple way to understand nonlinear optics is, for those of you who are at least familiar with crystal nonlinear optics, is that, when I come in with a pump, then because of nonlinearities and phase matching, I get new colors at different directions. So in a sense, the way I tune it is by changing the angle that the beam comes in. So now if I think of modes in an optical fiber, then they're basically different modes at different bounce angles, and that gives me a lot of degrees of freedom. The other thing that happens in a crystal is that, I get interaction only over a certain length. The same thing is true in an optical fiber. Different modes will interact only when they overlap well. And the nice thing about this overlap is that I can essentially write it as an orbital angular momentum conservation regime. And then finally, if I have pulses, then they all need to travel together, which means group velocities have to match. So I will use that last part to show you something interesting in Raman scattering. Usually in optical fibers, you do Raman scattering. What happens is that I have a soliton in an anomalous dispersion regime. Here's my pulse. As my increased power, the pulse kind of moves. And then at some point, if we notice, I have a little bump here, and that happens because now if one mode talks to another mode through Raman scattering, then that means that this one should be able to get gain in energy simply because the two have the same group index, which means they travel at the same speed, right? So if that happens, we image it. Indeed, it is exactly one mode order lower. And then as I increase power, all the power gets transferred to this new mode. So why is this interesting? Well, we can actually make a very versatile tunable laser with this. Here's an example of a 12-meter long fiber in which these are experimental results. We put a pump, so we get this first mode out of the fiber, and then we get the second mode, and then the third mode, and the fourth mode. And simply just by increasing the length of the fiber, we can change the mode that come out of the fiber. But more importantly, from a laser engineering standpoint, just by choosing different lengths, we can make lasers of different colors. The other interesting thing about nonlinear optics with these is that I can get Fourier mixing of different kinds. Fourier mixing is a phenomenon where I essentially, as the name suggests, four different waves interact with each other. So a pump can create a Stokes and anti-Stokes across a spectrum. I will show you later what this is useful for. But here I wanted to tell you about this very interesting phenomenon that happens with this, which is that this is Raman scattering. Notice that Raman scattering is strong for the left circularly or right circularly polarized light, but very, very weak for these optically active states that I told you about. So that was very interesting that we found that, without changing anything, without changing the power, just by changing the polarization, we can make Raman turn on and off. And when we saw this first, we said, okay, this is very interesting. Raman is usually a very robust nonlinearity. It happens no matter what I do. And in fact, the fact that it happens no matter what I do is what makes it useful for spectroscopy. But here somehow it seems to completely die. And the answer, the reasoning for it is actually very simple. If I send one of these pure orbital angular momentum states, here's the Raman I get. But if I send these optically active states, remember that the optically active state is one where the polarization of the light itself is rotating as it propagates. Well, if that's happening, then at two different wavelengths where Raman scattering happens, and at a different angular momentum mode, the chances that these rotation rates will match is very small, so that you get this walk off and you get this suppression. But that also means that there is one specific wavelength and one specific pair of angular momenta where this matching happens very well. And sure enough, for one specific very narrowband region, I actually get strong Raman scattering for one mode. This basically means that it's now mode dependent. So if I try to do Raman scattering with a pump in different modes, we indeed find that it completely follows this phase matching relationship. So to our knowledge, at least, this was the first time someone found a phase matching relationship for Stokes Raman scattering as opposed to CARS. And we're obviously interested because this may have some implications for some applications that I will end my talk with. Okay, so that was a brief section on nonlinear optics. Of course, I can give you an entire lecture on nonlinear optics, but just to give you a flavor of what how nonlinear optics looks different with structured light. Let's get to the applications. One of the biggest applications was something that the organizer already very kindly mentioned when he introduced me, which has to do with scaling the capacity of optical networks. Actually, it has to do with reducing energy consumption in optical networks. If I take any standard information system, then I can write a information capacity for it using Shannon's famous formula, that is the total capacity depends on the bandwidth and the signal to noise ratio. The signal to noise ratio is essentially power, right, for light. What this means is that if I now can increase the number of channels, then I can massively increase capacity, or I can hold capacity constant, and as I increase n, I can reduce power enormously because the power comes in a logarithmic path, right? So this is very interesting because this basically says that having multiple channels in which I send information is not only useful just to increase capacity, but perhaps more importantly, for a given capacity, it will help me reduce the amount of energy I consume. Similarly, in a data center, I basically a massive data center is one which connects a lot of different computer nodes. And today, to build one of these centers, you would need something like 192 lasers to connect everything. And lasers are very efficient things, no matter how much we love them. So again, if I had multiple paths, and by paths, I'm being intentionally obscure, but obviously one of the examples for a path could be the multimode fiber, these different paths that I was just telling you about. And that's the essential philosophy behind this. If I can use a medium to essentially create multiple paths out of it, it not only will help a lot of different applications we talked about earlier, but also will help with this energy consumption in networks. So that was our motivation. This was our first paper. This was, to my knowledge, the first time anyone had done DSP DSP processing free transmission of multiple modes down an optical fiber and show that you can actually transmit data. This was done back in 2013, and since then, across the world, a lot of people have done various different number of modes: 12 modes, 14 modes, 50 wavelengths, etc., etc. And this field has been burgeoning in this direction. Completely moving away from communications and data, the fact that I can create these states in an optical fiber means I should be able to create a grating such that I get the donut mode where I want, and at other wavelengths I get a Gaussian mode. That is essentially the definition of a stimulated emission depletion microscopy. The nice thing here is that we could get these images when this fiber was wrapped so tightly, which means that it may help for the first time to do nanoscale microscopy with an endoscopic system. Nowadays, if I had to do it, I have to go and sit in front of a big, bulky microscope. Similarly, a group with Jena in Germany had shown that you can use these fibers to taper it down so that a plasmonic radially polarized mode can have very, very, very high resolution, and so they're using that to build near field scanning optical microscopy tools. The high energy, different colors, those this weird group velocity match Raman scattering that I just told you about allows us to go to very high energies, very high peak powers directly out of a fiber. To give you an idea, out of most optical fibers, you can get maybe somewhere of the order of about tens of kilowatts of peak power. And usually when they say they make high power ultra fast fiber lasers, what they mean is that it's a pulse that is chirped and then they externally de-chirp. Whereas here out of the fiber, we can directly get very high peak powers. And this is something that we have already started using with our collaborators at Harvard Medical School to basically, this is the first step towards trying to build a portable probe by which I can look at nerve sheets on a hand. The Pancharatnam berry phase I told you about. again, because it depends on angular momentum and because these modes are stable there, if I had a fiber wrapped in a coil like this, and if I change this coil, look at what happens here. I change this coil, look at this image, these images rotate, which basically means that without changing the length, without being sensitive to temperature, without being sensitive to pressure, just being sensitive to geometry, I can actually measure a geometric sensor, obviously, out of this. And so this basically points to the fact that these modes have chirality can be allowed to use some kind of a measurand to measure and use it in some sensing or metrology application. Similar thing, because of this rotation, people have done magnetic field sensing, people have done multi-parameter sensing, and then we also made a spectrometer out of this because this rotation depends on wavelength. So we can actually make sub-picometer spectrometers that work at very high speeds because all we're doing is measuring an image. I told you about classical communications, but of course, if I were to do quantum communications is where I send a state in some superposition of states, an input which is a superposition of states, and I want to be able to switch between two different superpositions so that the receiver and the sender are the only people who know which basis they're sending the states in, and so no one can eavesdrop on it. That's the basis of quantum key distribution. And we demonstrated that because we have all these states, we can use orbital angular momentum as the state vector for this communications. And since that demonstration, again, people have shown that you can go to much higher dimensional. You can, in fact, use the randomness in the fiber to do actually a little bit of, random cryptography, and you can do a lot of other interesting things with this. Finally, remember I said something about how Raman dies and Fourier mixing remains. One of the reasons we are very interested in that is to solve a problem that everyone is trying to solve right now, which is have a system where use lasers that are well known. For instance, a pump at 1064 nanometers. It's a very cheap laser I can go and buy, and somehow connect a quantum memory, so a single photon in this wavelength range with a single photon at 1550, because that's where the fiber has lowest loss, so that I can connect a lot of different quantum memories. So the holy grail goal here is that if I can connect a lot of quantum memories, I might be able to do much higher dimensional quantum computing, much faster quantum computing. In fact, if you look at Shor and Grover's algorithms, they point out that qubits and qubits can do much better if their dimensions were much higher. So we want to see if we can make a device out of this. Here's the pump. Nice thing about the modes that we have is, I have a lot of these different modes. That was the whole point of having this topological guidance, which means that I should be able to do Fourier mixing between different wavelengths at different points. That's exactly what we did. We put the pump in two different modes, and we would get either Stokes and anti-Stokes here, or we can do a different variation of it. The main point of all of this is that if I look at the biphoton correlations of each of these, then I can either get anti-correlated, correlated, or uncorrelated biphoton correlations. For those of you who are familiar with the quantum aspects of optics, you will immediately recognize that these kind of states are useful for entanglement. Suppose I want to entangle two different quantum memories, and these kind of states are useful for heralding. Suppose I want to use a click on a detector as a means of knowing when I should do the next quantum logic operation, right? So each of these states are important for different cases. And what's exciting for us is that just by using one fiber and only one spatial light modulator, we can switch through and make all these functionalities happen at the same time. We haven't demonstrated quantum computing yet, and that is our goal, hopefully, with these states, or demonstrated that we can connect two quantum nodes yet. But the first step towards that is to ask, what is the coincidence to accidental ratio of these, which essentially is a noise figure of some sorts. And in quantum optics, they say that if you can do better than 10, then this system can work. The fact that we can go up to several hundreds is very encouraging in using these systems to build quantum networks. So that brings me to the end of my talk. Hopefully, what I showed you is that all these individual exotic modes, when you mix them there, then you do some kind of signal processing, then you get a lot of applications. But each of them actually has a lot of rich physics in them, right? They have their own chirality, they self heal sometimes. And as I mentioned, they even allow guidance in a regime where, all our textbooks say you need total internal reflection for guidance. I just showed you that you can completely avoid that. And so it's a very exciting area with a lot of different possibilities, and I'm sure a lot more to be found yet. And obviously, because of the variety of different unique properties, it has found applications across most of the areas that we tend to try to impact, at least in one way or the other. Um, Everything I described was work not done by me, but by a very, very talented set of current and former students and postdocs, and I'm indebted to them for the fantastic work they have done over the years in this regard. The right side has a lot of people who were key in some of these papers who have since graduated. The left side has people who are still around. And of course, this was not just an effort at our own school. It involved collaborators from practically everywhere in the world. I can pretty much point to every part of the world in this list here. And even so, I might have inadvertently missed some. The work, of course, has been possible due to the support of a lot of different funding agencies over the years. And most importantly, I would like to thank all of them. Most importantly, thank you for your attention. And I'll go back to the summary slide and I'll stop there. Hello?
Hello. Thank you, Professor Ramachandran. And Professor RP Singh is here.
Yeah, we are here.
Yeah, so you can hand over the question answer session to Gautam.
Yeah, he is going to handle that.
Yeah. Hello.
Hello.
Yeah. So thank you for a nice talk. Now I'll take the questions from the audience, if any. And I see some people raising hand. Perhaps you can see also some people are raising their hands. Who is having the mic? Can you just? Is he audible? Can you hear?
Yeah, I can hear.
Yeah, go on.
We cannot hear from the audience.
That mic is not working?
Let them come to podium.
Hello, Professor. I have two questions. The first one is that you explained a lot about the scalar form of self-healing beams like Bessel and probably that air beam also. What about the vector aspect of such beams? Like if we give a polarization degree on that such kind of beams, how we can utilize like in real world like applications? That was my first question.
So I mean, that's an interesting question. Can you hear me? Can everyone hear me?
Yes.
Yes.
Yeah, okay. Yeah, so that's an interesting question. What does polarization do to it? Well, it all really depends on, I think polarization plays a role only when you go to, so polarization can play a role, fundamental role only in two circumstances, right? One is when I'm focusing something tightly, because as I schematically showed, when you focus something tightly, then the polarization vector rotates, which is kind of a very hand waving way of saying the same thing that the atomic physicists have said much more precisely, which is that when I focus something tightly, I get spin orbit coupling. And once I understand that all of this is about spin orbit coupling, whether because of a potential well with some gradients or because of focusing, then I understand that polarization will actually not play a role unless not play a fundamental role in focusing these beams unless you go to the regime where you focus them very tightly. But once you start focusing them tightly, you can get some very other exotic effects where you cannot separate the spatial structure from the polarization. I mean, to some extent, that kind of you can see that in this LS coupling that I was telling you about, right? The different propagation constants for different modes depends on whether the angular momentum and spin, orbital and spin angular momentum are aligned or anti-aligned.
Yeah, but what about like if I focus bezel beam, which is like a if I focus in a Fourier plane, I will get a perfect vortex kind of structure. And if I use like a spatially varying bezel kind of beam, what is your comment? I mean, in that area, is it like something useful to pursue kind of thing?
I mean, that depends on what exactly you're doing. I mean, the thing that you suggested is a very general problem. Focusing a Bessel beam with yeah, I mean, I don't quite, I mean, it'll depend on a specific application. I don't know what exactly you would use it for. I'm sure there are some applications to it, but and I think it's also very specific to what you're trying to do. That may
Okay,
determine.
there was like a connecting question. Okay. The other question is, so how we can visualize the geometrical phase, because the other phase, like dynamic phase of light beams, we can like visualize like the sinusoidal wave, and it is that phi like a little bit movement near and away to that x-axis x origin, and in the case of the polarization, that ellipse orientation angle is something like if you took like XYZ axis, angle and Z propagation, then some angle. So, but in geometrical phase, always like I understood like in Poincare sphere, there will be like some like non-zero area it will cover in evolution, and that area will be related to this geometrical phase. But is there any other way to like visualize such kind of a beam in in the previous?
Yeah, I mean, for me, actually, the most physically intuitive understanding of geometrical phase actually comes from the angular momentum content of light. If you have something that has 3D, that has if you have something that subtends a 3D path, subtends a solid angle, and essentially has a 3D path associated with it, right? Then, in a sense, it is that the path itself has angular momentum associated with it, right? Because the fact that the path itself is doing something weird, uh, so think of it as the path imparting angular momentum. So now if my eigenstates can only be of this angular momentum and this angular momentum and this other angular momentum, then the fact that the path imparts angular momentum gets manifested as this mode breaking up into this mode and another mode. It's exactly the classic mode coupling phenomenon, except that it's very, very specific in that it breaks into its degenerate state and essentially picks up a phase. So that's the reason why the Pancharatnam Berry phase is exactly related to L and S, the amount of orbital and spin angular momentum light carries.
Okay, thank you, Professor.
Sir, my question is related to downlink and uplink scenario in satellite quantum communication. So the two major problems while dealing with Cassegrain telescope, while it is transmitting on receiving telescope, we have some geometrical losses in like LEO, MEO, and GEO communication. So mainly in GEO, it is challenging how to mitigate these effects like beam spreading and beam wandering effects. So these are major challenges in getting optimum performance parameters. So how to mitigate these effects? Beam
Yeah, I
wandering.
mean, so I mean, obviously, I'm sure you're aware of different ways by which people have been trying to mitigate these effects, including adaptive optics and beam tracking and things like that. One, I mean, in the context of the talk that I just gave, one emerging question people are asking is whether, at least for communications, whether it's quantum or classical communications, um, whether you try to counteract the effects or you try to build redundancy into the system, right? So what would redundancy in this case mean? I put the same amount of data on different channels, or I take the data and split it into different channels. Now, what are these different channels? There will be spatial modes of different kinds. Then the probability that I will lose all of them is much smaller than the probability that I'll lose a sum. And so with that, hopefully I can essentially build up a system. Another way of thinking about this is as follows. Imagine that I encode a bit, classical or quantum bit, into a mode. Yeah. So classically, we think of this as, let's say a bit is 1 or a 0, right? Now, it's not only 1 or a 0, but I also tell you that no, it's in the orbital angular momentum state L10 and not in L20 or not in L30, right? Let's say for example, let's just take 10 states, right? It could be in L equal to 0, 1, 2, 3, 4, 5, 6, all the way up to 10. So this single photon could be there, could not be there, and it could be in any one of these states. So in other words, what I have essentially described to you is a much larger alphabet of information. The information is no longer just 1 or 0, but it's a 10 base information. So now when I detect this, I get a lot more information out of this system. And so if you've heard of a concept called pulse position modulation that people use in telecom a lot, then this is essentially very similar to pulse position modulation. In the quantum world, what we're basically saying is now, by knowing which mode it came in, the photon came in, I actually have 10 times as much information than I did.
Okay.
So
Thank you,
yeah.
sir.
Any more question? Anyone having? Anyway, so I have one question to ask you. So you were saying that this is Gautam. You were showing something with the multimode when you are bending different vortex or vector vortex, anything that is having distortion, but when your order is something around 5, it can survive that bending and other thing. But whereas in case of free space propagation, where people have shown that if you have having a vector vortex beam, it can withstand all the perturbation while propagation. So what is the basic difference? Means why in case of fiber only the vortex is surviving the perturbation due to the bending, whereas in case of free space, it's a vector beam is serving the purpose.
Okay, I mean, two answers to that. I don't completely buy the idea that vector vortices in free space are stable. I'm aware of a lot of that work, and when they say it's stable, they're basically saying that if I look for the singularity, then I can still find the singularity.
Yeah.
Which, I mean, I think it's interesting. The physics of the fact that you can find the singularity still is interesting, but the reality is that the information carried in the beam has been highly distorted, right? So from an information capacity carrying standpoint, whether quantum or classical information, or from a sensing standpoint, I would argue you haven't been able to maintain them in free space. Now, having said that, the question then really to ask is not why only certain states are stable in a fiber, whereas a lot more of these states are stable in free space. I would flip the question around and say, why are certain states stable in fiber when none of these states are stable in free space? So if we start from there, then the answer actually becomes very much related to the spin orbit coupling. Because of spin orbit coupling, and that's something that doesn't happen in free space, the propagation phases of those two get separated just enough so that as I go to higher and higher order states, L is larger, the spin orbit coupling is larger, so they remain further apart. Whereas in free space, of course, they all have the same propagation constant.
Okay, thank you. Any more question? So if it is not, then I think Lokesh can take the question from other audience.
Yes,
Gautam.
Yes.
There's one question in the chat box. You may take it if you wish.
Yes, sending.
Just let me check that.
But I should say thank you for that question. I mean, I do think that's a very interesting question as to, you know, in which and you know, there's still a little bit of debate. I mean, I think it's still a very interesting question to ask as to which model basis is stable in which medium, and it has a lot to do with whether what kind of angular momentum the medium itself imparts.
Okay, yeah. So I see one question in the chat box. Just a out of the box question. We have term in Schrodinger equation which represents a phase. Can the phase store information? There is a question Surendra Singh has asked to you. You can perhaps see the chat box also in case.
Yeah. I just opened the chat box. I'm trying to parse and understand the question just out of a box. We have a term in Schrodinger equation which represents a phase. Sure. Can phase store information? I mean, my simplest answer is yes. Phase is the only thing we store information in. In fact, more so than amplitude. It's been a very long time since we've made any kind of communication system, classical or quantum, where we store information in amplitude, because you know amplitude is very hard to measure. Phase is very easy to measure with interference. So, but I'm not sure what that has to do with the term in the Schrodinger equation which represents a phase. I mean, eventually this is the phase of the eigenstate, right?
I don't think any more question is there. There is another question from Professor R.P. Singh. Please.
Just wanted to know this optical fiber, this special fiber, how long this optical vertex can propagate. 1 kilometer, like 1.1 kilometer, your science paper. After that, whether length has been increased or 2 kilometers, 3 kilometers, how far this kind of fiber?
It's a very good question. The longest we have gone with this is 13 kilometers, and the that was with states that used to have orbital angular momentum of around 6 7 5 6 7. So the L was 5 6 or 7. But as I just showed you earlier today, that with this topological guidance, now we can go up to angular momentum states which are at up to L equal to 40 50, some really high angular momentum states. And we have not yet gone long lengths over it. We've gone a kilometer in those, but we measured the crosstalk per length, and we found that the crosstalk was around 40 dBs per kilometer, which basically means that if you do the calculation, we should be able to go 100 kilometers of these now.
So
But we haven't done that yet. But based on the crosstalk, we really I think we now have. So the whole idea is, this goes back to the earlier thing that I said, right? Because of spin-orbit coupling in all these systems, the higher, and it's very counterintuitive, the higher the angular momentum state, the more stable it is, and the more and the fact that now we're suddenly in the 40s and 50s range is where we think why we naturally got much better stability. Having said that, we haven't demonstrated 100 kilometers.
So what is limiting? Like it's 9 years now. It's 13 papers. So what is limiting going beyond like kilometers, like 30 kilometers, 50 kilometers, or 100 kilometers? As you say that you think you can take it to 100 kilometers, but what is the limiting factor? Why it is not like moving beyond that? Yeah, it's 9 years now. Yeah.
Yeah, I mean, maybe we're all too slow. I don't know.
It happens. Yeah. Okay.
So there are two answers to that question. One is what is limiting. I think I would say one answer to it is that a lot of applications where people have been interested in them right now were data center type applications, right? And in space division multiplexing, which is perhaps one big application, the biggest. I was just at the European Conference on Optical Communications, which was last week. Which is, as I'm sure you know, one of the two biggest conferences in the world in the area. It was more and more clear that, I mean, space division multiplexing is first going to happen in amplifiers, and amplifier lengths are 100 meters or 10 meters or 50 meters. So it could be that a lot of that's the reason why, since data centers and amplifiers are very important, most of the demonstrations and people who have been working on it have been kind of playing around the 1 kilometer level, saying that if you do 1 kilometer, then you've done data centers and amplifiers and switches and everything but long haul, right? So I think that's one answer to the question. The second answer to the question is actually, I don't know. I mean, if you had asked me this question 2 years ago, I would have said that I wouldn't ever predict more than 10 kilometers out of this. We have demonstrated 13, maybe 10 metro area distances is what this could work in. But like I said, in the last 2 years, we have suddenly found that we can get up to 40, 50 angular momenta, and they seem to be very stable. So I think now at this point, we hope to get there to the 100 kilometer regime.
Thank you.
So,
No, there is no more question,
okay.
and I think you can take it over.
Yeah. So thank you, Gautam, for very nicely handling the question and answer session. In case someone from WebEx would like to ask a couple of questions, just last call. So thank you, Professor Ramachandran, for a very interesting presentation and also giving valuable time for the question and answer session. So before we conclude the session, I invite my colleague, Professor Navinder Singh, for the word of thanks. Navinder, over to you.
Thank you, Lukesh. Am I audible?
Yes.
Okay, so, yeah, so it's my pleasant duty to conclude this session, which is a part of an ongoing students conference, PRL Optica Students Chapter. So it was a very illuminating talk on higher order angular momentum beams, adaptive optics, analogs of spin orbit coupling, chirality, novel applications of these spatially complex states of light beams. So, so now I would like to say thanks to all involved in this PRL Amrut Vyakhyaan series. First and foremost, on behalf of Amrut Vyakhyaan committee, I would like to thank today's speaker, Professor Siddharth Ramachandran, for taking time from his busy schedule and delivering this excellent Vyakhyaan, and also for patiently addressing all the questions and comments from the audience. Next, I would like to thank Professor Nandita Shrivastava for spearheading this series with her constant efforts and enthusiasm. Also, thanks to Professor Nelu Bharadwaj for inspiration and guidance. And thanks to Professor Palam Raju for his guidance and efforts to keep the series going well. Special thanks to Professor R.P. Singh and Gautam Samanta for their help in today's Vyakhyaan. With this, we come to the very end of today's session. Now we will be signing off from this platform. I hope to see you all next Wednesday with yet another interesting session. So thank you very much and good evening to all of you.
Yeah.
Just
Thank
a
you
small
again for
announcement.
this
Just a
opportunity.
small announcement for the audience. Next week we will have Vyakhyaan on Thursday instead of Wednesday.
Yeah.